All right, good morning, kids. We're going to talk about numerical data. There was a previous video that talked about stem plots, so make sure that you've seen that video. And we're going to pick up from there to talk about our quantitative data sets. So we've seen already in this class dot plots. First day of school, we had our random numbers 1 through 4. We've looked at other dot plots in other contexts, and these dot plots are really nice when we have a few data points, right? Less than 50 for sure. And there's clearly less than 50 here in these different data sets. They're really nice, quick to construct. They're good for an AP student, and they're the ones that we're going to make probably most often, especially in the second semester. However, they can go wrong. If we have too many data points, we lose all sense of what we're really looking at. This is way too hard to see frequency. We couldn't possibly count all these dots to know the frequency. And if that happens, then we're going to switch over to what's called a histogram. So here's a histogram of the data, and it's much easier to read. And we can have then a frequency list here on the side. So we have an idea of frequency with our histogram. When we look at dot plots of test scores, here's a group of test scores from several years ago to protect the innocent. But this is test scores for test 1. And we can see that we had 2 students that scored 100. We could see the individual scores. So we could pick out any one of these and know what that student scored with our dot plots. If we change that to a histogram, histograms have something called a bin width. And so in this way, we have a bin width of 5. These are 55. We always include the left endpoint, and up to but not including 60. So these are really like, for the sake of test scores, 55 to 59, because we don't have any scores that have parts of points. And then there were no scores between 60 and 64, but these scores could have been 65, could have been 66, could have been 67. These are all the scores between 65, including 65, but less than 70. That's this bin. And so that works its way all the way up here, and we can see that when we get to this bin, then we have this bin that's includes 100, but is less than 105, and if you didn't know anything about test scores, it would look like it was possible to get over 100 on here. Because we really don't know where these scores fall within this bin. It may be misleading a little bit, but we just know that there are 2 scores that are at least 100, but less than 105. We go back to the dot plot, and we can see, oh, they were just hundreds. So we have a lot more information here, but when we get to the histogram, we lose some of that specificity. We can see that there were 8 people who scored between 85 and 80, up to 89 really, but we don't know those individual scores. So that's a weakness. Changing the histogram's bin width, we can certainly, here's a dot plot for hair lengths. We can take that dot plot for hair lengths and change it into a histogram. We can, here the bin width is half of an inch. Then we go up to an inch, and you can see it smooths out a little bit. We don't have as many gaps, so maybe this graph is a little bit easier to look at. We can increase it to 2 inches. That's maybe better, but we're starting to lose that specificity that we talked about. We can increase it to 5 inches. Now, that's a big range of hair lengths. 5 inches is pretty long, so we have people who are essentially bald all the way up to 5 inches, and there's a lot of those, and this is probably many of the males' haircuts and some of the females. We do have some crossover there. So you can see there's 2 groups here with our data, longer hair and shorter hair. When we look at histograms to the untrained eye, they look very similar to bar graphs. However, there's some key differences. Bar graphs have gaps. These are categorical. The order of a bar graph, we could switch. There's nothing that tells us we have to start with first. We could have started with the crew. We could go in any order that we really want to. There is a logical order to this, but we don't have to follow that with a bar graph because they're just categories. With a histogram, we're on a number line, and we have to go in that order to follow the number line. All right, so we're going to learn how to CUSS and BS in this class, which is one of my favorite things when we're talking about data. And sometimes when you're looking at data, you know, like this ugly graph that we had here, you may want to CUSS and BS about this anyway until we start to really do more work with it. But when we're talking about CUSS and BS and AP statistics, what we're really talking about is identifying and describing these numerical distributions in a really profound way. C is going to stand for center. And there are three measurements that we use for center generally. We have modes, which is just the most frequent. We have the mean, which is the average, which we've talked about already in this class. And the median, which is the middle number in a data set, which we'll talk much more about when we get to box plots. So measurements of center. Sometimes it's hard to read the center, and if I scroll really quickly back here, if I don't have the individual scores and I only have this histogram, I probably couldn't tell you exactly where it is. I can say there's a mode somewhere between 85 and 90, or I can say centered near 87, and that's the only time we really use that generic centered idea is when we really don't have a sense of what the numbers are and we don't have a way of doing that. But mode would work here. But I can't really talk about a median score, and I don't really have access to the mean. So we could talk about mode or just use a generic centered when we're talking about that. All right, so next is shape. And when we talk about shape, there's several that we think about. Unimodal by itself isn't a shape, it's just a feature of a graph. Bimodal generically is a shape. Symmetric can be a shape, but there's a lot of symmetry in different graphs, so usually symmetric and unimodal go together to give us a shape. Skewed is a shape, and we can have different directions for skewed, and then uniform. We're going to draw those in a minute, so you'll have a list of these with a picture, but these are the shapes that you need to know to start this course. We're going to add one eventually that's like a really important shape for us in AP statistics called approximately normal. So center, shape, spread. So you can see the C and the S and the S. All distributions of numeric data are going to have a center, shape, and spread. So spread, if you were in elementary school, the minimum you could do is just talk about the min and max values. The data will go from 3 to 50 or something like that. When we did more with that in middle school, we would say the range, and if we're going from 3 to 50, it has a range of 47. Be careful how you use the word range. The range of a data set is a single value. So you don't want to say that the data ranges from 3 to 50 because that's a misuse of the word range. IQR we'll talk more about when we talk about box plots, but that's a measure of spread or standard deviation. And when we talk about measures of spread, when we use IQR, we're usually using the median for center. And if we use standard deviation, we're usually using the mean for center. So we kind of save those. So if we talked up here about center and we talked about the median, I wouldn't use standard deviation. And if I talked about the mean, I wouldn't use IQR. So those are usually reserved for that. The U for CUSS is unusual features. And so if there's anything weird happening in the distribution, any gaps, any possible outliers, we would also mention those, but not every distribution has those. So again, if we zoom back here, there's a gap. There were no scores from 60 to 65, or in that bin from 60 to less than 65, which makes this group of score, this one person that scored maybe as low as a 55, a possible outlier. We're going to have a test for outliers soon. So when we get to that test for outliers, we'll be able to identify it really concretely. But in the meantime, we usually just say possible outliers until we know for sure. And then BS is be specific. So we really want to be specific when we're talking about our data. We want to be in context. This be specific part, really context is a really important part of this. So if the data set is about hair lengths, we want to say that the median hair length is that the hair lengths start at 0 inches and go to 55 inches or whatever we had in that slide. I don't remember now, but context and constantly bringing back the context of whatever the data set is measuring is really important. Okay, so here's our shapes. And our unimodal shapes really come in a few flavors. So when we talked about this, unimodal could be lots of things. All it just means is there's one mode. So if we had unimodal and symmetric, the data may just kind of do this, okay? If it's not symmetric, it's going to be skewed. And so we could have data that's stretched out to the right. So here's my x-axis. Or we could have data that's stretched out to the left. So this data set stretched out to the right, we could have something like income in the United States, right? Most people are not making very much money compared to the ultra wealthy that are way down here. And this would be like stretched way over here. This could be more like test scores that we saw on the most recent test where most people did very well and only a few people didn't. And so it's pulling the mean down and stretched to the left, okay? So this is skewed right. And you can just see it's pulled to the right. Otherwise it'd be symmetric. So it's like which way is it stretched that makes it not symmetric. This is stretched to the right to make it not symmetric. This is stretched to the left, so we say skewed left. And this is just symmetric. Now, bimodal can also look kind of symmetric. So if we had this bimodal distribution and it looked something like this, that can look symmetric. We can divide it in half here. We can have some symmetry. Not all bimodal distributions are symmetric. We can certainly have a bigger data set and like a little one, and that could be two modes as well. But what we're really looking for are two distinct peaks, and they're peaks that we can describe. Why are they there? Right? We need to be able to, if we identify something as bimodal, we need to be able to identify why there are two modes. Otherwise, it could be just variability. Like this mode here may be an actual mode of another group of students or something, whatever we're measuring. Or it may be that it's just variability in our sample. And this is just an odd bump of data that we got just from the sampling variability. And if we can't explain it for a clear reason, we would not call it, I would just say skewed to the right. Instead, I won't call it bimodal unless I can identify why there would be two modes. That's really important. If you're going into multimodal distributions, have a story to tell. Why would there be two different groups of data? When we're talking about modes, we really have a group of students here, or whatever we're measuring, group of students here. This could be like a more challenging test where we had people that didn't perform so well, and then a group of people that studied and did perform well. Maybe that's probably more like a quiz than a test, but that happens a lot. Okay, so there's bimodal, and then if we're talking about uniform is, this is like usually like, what is it mostly? So if we were talking about uniform, we would have a distribution where every bin had about the same frequency in it. And so this is looking uniform where it didn't matter the input. We're going to have about the same output. Okay, so that's how uniform is looking. Now, I don't know why this is happening. If we had something that was a little bit off, I would still say that this distribution is mostly uniform or roughly uniform. I'm not going to let that one bin ruin what's happening for most of the distribution. So we can say this is roughly or fairly uniform. That's the best descriptor for this shape. I wouldn't just say, oh, it's skewed to the right. Okay, so there's our shapes that we have to know now. When we get to this symmetric and unimodal graph, eventually we're going to be talking about approximately normal, but we don't need that yet. So if it's a unimodal, what about symmetry? We always say roughly symmetric or approximately symmetric, unless you happen to know that it's perfectly symmetric. There's a lot of these descriptors where we're going to put in roughly or approximately or fairly just to save ourselves from really a lot of criticism. So when we fold this, you can see it's not perfectly symmetric, but this is roughly symmetric. We talked about skewed left and skewed right. This distribution of ages for cardiac patients is skewed to the left. Otherwise, it'd be symmetric, but we're getting pulled to the left. Distribution of charges based on cardiac patients, how much they're spending, oh my gosh, it's dark, is to the right. Okay, this is skewed left. The tail is going to the left. This is skewed right. The tail is going to the right. Okay. We can also say skewed negatively because the negative numbers go to the left. We could say skewed positively, the positive numbers go to the right. You can only use the word skew when we're talking about the shape of a distribution. Be really thoughtful about the vocabulary and how you apply it. Okay, I already mentioned this, that we're going to say possible outliers for one homework, and then we're going to get into a way to be able to test for those. So I would say possible outliers here. I really don't know if that's an outlier until I have a way. All right, so there's some practice. If you're doing this at home, you can pause the video after these and try it. I would recommend that you at least talk through it if you're not willing to write it, but writing it is going to be a better prediction. So when we cuss and BS about this distribution of quiz scores, we're going to go through a checklist. And when I grade these kinds of things, I usually do that as well. So here's your distribution of quiz scores. In class, we would have had students writing. And then I'm going to give you a second. You can pause it, and then we'll look at the solution. All right, so here, for shape, we see a bimodal distribution. There seems to be two groups. And this I kind of hinted to earlier when I was drawing bimodal. We have the students who studied, prepared, and ready. We have students who are less ready. And so there are two groups of students for this quiz. And I can tell a story, so I'm going to call it bimodal. This isn't just variability at work. So there's my shape. Center, distribution of quiz scores has two modes. One around 55. There's the mode right there for 55. And one around 80. Okay? Notice, I don't know if it's exactly 55 because I don't know the bin width. I can't really make that out. It's like maybe 2.5 points or something. So we're just going to use this modifier of around or approximately. Spread. The spread is from the mid-30s to the mid-90s. If you wanted to use range, remember range is a number. I don't know enough about the values here to come up with IQR or standard deviation. So those are off the table right now. So we have center shape spread. All distributions will have center shape spread. Not every distribution has unusual, and if it doesn't have anything unusual, you don't have to say anything. But I do notice that there is a gap in the lower 40s with a possible outlier in the mid 30s. Okay, so there's all our stuff, and when I grade this, I would just write CUSS right down the margin and check them off as I read it to see that you have it. Notice context. We have quiz scores here. So when we're putting in this context, then we at least, we got to hit it once in the whole thing. I'm looking for you to make sure that you're being specific about what you're measuring at least one place. Okay, here's another distribution. Pause the video. Take a second to talk about grades on probably a test, it looks like. Give you a minute. Okay. So the shape here is skewed to the left. We do see a few peaks here, but this is just normal variability that we would expect in a small sample of scores. So just because we have bumps in the data doesn't mean that those are multimodal. We're just going to look at the overall trend and say, wow, this is really pulled to the left, especially with this score here. But even without it, it would be skewed left. The spread is from the mid-50s to about 100 for a range of 45. Center distribution of grades has a single mode around 100. You could talk about that. If you wanted to say center, like where is the rough center of the distribution, you might pick something that's more like either low 90s, high 80s, and you could say centered near, and that would be okay too. So either pick the mode or centered near here for the typical student, because that's really what center is going to describe for us most of the time, is what did the typical kid do. And lastly, there is a gap from the upper 50s to the upper 60s with a possible outlier in the mid 50s. So we just check them off. The order that you put these doesn't matter. If I were doing this, I would have CUSS, BS, and I would go through and say, oh, there's shape, there's center, there's spread, and unusual, and we're looking for grades, and they got it, so we're specific, right? So that's how it's going to be graded when we go through and do that, both for homework, quizzes, tests, all of that. Okay, comparing distributions. Now, this is really, really important. You may have two different distributions, and the prompt, instead of saying describe the distribution, is going to be compare the distribution. And when you compare distributions, you have to use comparative language. We're looking for language like higher than, lower than, similar to. We want to compare them. So if we're comparing the centers for the distributions of female and male heart attack patients, we would say something like the mode for females is in the high 70s, while the mode for males is in the upper 60s. And that by itself isn't enough. We have to say, oh no, we said higher than. So mode for females is higher than the mode for males, upper 70s versus upper 60s. Okay, U.S. President stem plot from last time. Here's our stem plot. This 7 needs to be moved over here. If we're going to compare the distributions, we want to use comparative language. It gives you a chance to pause it. And then we're going to say, okay, distribution of inauguration ages has a mode in the 50s, while the distribution of ages it has a mode in the 70s and or 60s and early 70s. That is not comparison. Okay, not enough. You're just going through and doing a reporting of each thing independently. If you want to compare them, you have to use higher than or lower. You can go with it, say this mode is lower than that mode. That's fine, but you have to use comparison. Okay, age at death has a more spread. There's a larger range of values here than the age of inauguration, and we're giving stats. Everybody see it? Give stats. So, skewed in which way? Because we have these back-to-back stem plots, we got to pay attention to the number line here. Okay, so we're going from 3 to 10. When I draw this distribution, it's getting stretched towards the lower numbers. This is skewed left, lower negatively. So is this distribution. It's skewed towards the lower numbers. So even if you turn your head, when you turn your head and look at this distribution, it is going left. If you turn your head and go look at this distribution, it's going right for the way that the numbers are, but it's actually skewed towards the lower values. So you really got to be careful about that. They're both skewed in the same way. All right. As a wrap up, don't CUSS and BS for categorical data. We only do this for numerical data. Do not CUSS and BS about categorical data. With numerical data, we can't just move the categories around. We're stuck, so we can actually talk about shape. If we can move the categories, it doesn't make sense to talk about shape. So don't CUSS about categorical data. All right, in class we would have a quiz. You're not going to. That's the lesson.